Hello everyone. In this video, we're going to wrap up the PID controller series by adding in the derivative component. What you're seeing right now is the system running with the derivative component added. As you can see, the result is a fully functional and stable controller. If you're new to this series, then I highly recommend watching the first 3 videos first, before continuing, since each part builds directly on the previous one. This is the block diagram of the controller with the derivative component added in. This block diagram is the same one used last video for the proportional controller, but with 2 additional modules. The first module added is the second error calculator, shown here. The second module added is the derivative response block, shown here. In this video, I'll show you exactly how to add the derivative component by implementing these 2 modules. The new error calculator module, shown in the pink box, will be used to determine the old error. The old error will then be used as an input to the derivative response block. Thankfully, to implement this module in code, all we must do is instantiate another fixed point subtractor. So now let's take a look at how this is done in code. So on lines 81 to 91, we implement the second error calculator module. On line 84, we set the parameters to match the subtractor instantiation used for the first error calculator. It's important that both subtractors use the same parameters so that they share the same bit width and radix, ensuring that the results are compatible. For the inputs of this new instantiation, we again use the desired distance, but this time we subtract the previous measurement instead of the current one. Since the previous measurement signal is unsigned and only 16 bits wide, we convert it into a signed 17-bit value by appending a leading 0. Finally, the outputs of this module are connected to the old error and old error done wires that were declared earlier. To implement the derivative response, we simply just execute this mathematical operation in hardware. KD times the difference between the error and the old error, all over time. Thankfully, to implement this change in code, all we must do is instantiate a fixed point multiplier, a divider, and a subtractor. These 3 arithmetic modules, when instantiated and configured correctly, will implement the derivative response. So now, let's take a look at how this is done in code. On lines 114 to 125, we compute the error difference by subtracting the old error from the current error. This is done by instantiating a signed subtractor. On lines 128 through 151, we divide that difference by t to obtain the error difference divided by time. The divider is configured to accept S32.32 inputs and produce an S64.32 output. Note that both the error difference and the elapsed time are passed into the divider using expressions that convert their radix to be compatible with the divider. On lines 153 to 167, we multiply the result of the division by KD to produce the derivative response. The multiplier is configured to accept S64.32 inputs and generate an S160.32 output. Since both the quotient and KD are already in correct format, they are passed directly into the multiplier. Lastly, on lines 170 to 182, we add in the derivative response using a 3-input signed adder. To make the derivative response compatible with this adder, it is sign extended and aligned before the addition. At this point, no additional modifications are needed, and the derivative response is fully implemented. With these changes in place, the controller is now fully functional. Here's the system running again. So far, what we've built only includes the proportional and derivative components. The next question is how we would implement the full PID controller. To do that, we simply add a module for the integral response. The integral response is just a running sum of the error multiplied by Ki. In practice, however, more is usually required to make the integral response usable. For example, clamping is needed to ensure that the integral term does not grow indefinitely. In addition, stabilization techniques are needed to control when the PWM module is driven. For instance, if the ball is very close to the target position and stays there for about 1 second, we no longer want to drive the PWM controller. This prevents noise from causing sudden jerks that can push the ball away from the desired location. One of the main reasons the PID controller is not perfect is that the servo takes a long time to respond. Here is a video showing just how slow it can be. As you can see, when the servo needs to move from one extreme position to the other, it takes long enough that we can easily perceive the delay with our eyes. This is a major problem because in an ideal controller, the response would be instantaneous. There are two main ways to increase the servo speed. The first is to power the servo at 5 volts, which increases its speed according to the datasheet. As you can clearly see, when we power the servo at 5 volts, it moves much faster. While using more voltage speeds up our current servo, the better solution is to use a more expensive servo that is much faster. In addition, because the servo arm is offset to one side of the beam, the ball may move faster in one direction than in the other. By properly calibrating the PWM module's center position, this mechanical nonlinearity can be largely cancelled out. In the ball balancing demonstration you saw earlier, the PWM module was calibrated with a value of 150,000. For your own setup, you will need to experiment with this value to find an appropriate center position. You should also remember to adjust the upper and lower limits of the PWM module to match this center condition. These lines show where those changes need to be made. So there you have it. We've now successfully built a PID controller using the proportional and derivative components. I'll leave it as an exercise for you to add in the integral component. As a quick warning, the integral term takes time to become usable. Clamping and stabilization are required to prevent instability and ensure smooth performance. That said, the effort is absolutely worth it because implementing the integral term will give you valuable experience building a non-trivial, real-world control system. For those of you who bought the book, downloaded the 3D print files, and built the beam, this is a great next step. All of the code from this video and the previous videos are already provided. All you need to do is just add a few additional modules. With that, I'll see you all next time.